everyone to our first seminar. Today we have Tristan Collins, who's visiting us from the University of Toronto, and he will tell us about Calabi-Yau metrics, from Calabi-Yau metrics to optimal transport. Please.
Okay, well, thank you very much, and thank you for the invitation. It's very nice to be back. It's been a while since I've been at the CMSA. So I'm going to talk about this sort of connection between complete Calabi-Yau metrics and optimal transportation. And this is going to sort of start as a geometry talk and slowly turn into a talk about optimal transport. But I want to try to give some, so that it's turned out that the sort of techniques for these two problems have sort of helped each field independently. So I want to explain some of that work. So let me start with a theorem, which is the sort of motivation for this talk. There's a theorem of Tong and Yau from 1990. So suppose you have a compact, so X is a compact complex manifold. And suppose that the anti-canonical bundle, the top wedge power of the tangent of the holomorphic tangent bundle, is ample. Okay, so that means it has a metric with positive curvature. So in other words, one says that X is phono. Okay, so then suppose you take a smooth divisor. Smooth, reduced divisor. I'll give examples in a second, right? Smooth reduced anti-canonical divisor. So it's the zero of some section of this line bundle, some global holomorphic section of this line bundle. Then you can look at y minus d. So y is x minus d. So you look at the complement of d. On the complement of D, so this is the zero set of some section of the dual of the top wedge power of the tangent bundle. So you can invert that section on the complement of D and get a holomorphic section of the canonical bundle, which makes this a non-compact Calabi-Yau manifold in the sense that it has trivial canonical bundle. So then, so what Tong and Yau showed is that this admits a complete Ricci flat Kähler metric. Okay, so this metric is very interesting. I mean, it arises when you study, in fact, degenerations of compact Calabi-Yau manifolds. Has sort of geometric bubbling along certain degenerations. So I'm not going to talk about the compact case so much because I want to get to the other stuff. But this is a theorem which is a major result in the field. And I'll just say that it's very easy to cook up examples despite all the assumptions in this theorem. So for example, if you take X to be CPN, any degree, let's see, any polynomial P, generic polynomial of degree n plus 1, then you can just take the zero set of P. As long as this is generic, its zero set will be smooth and reduced. So this is you can look at the complement of the zero set of this polynomial inside of CPN, and that admits a complete Ricci flat metric. And this is kind of interesting because, of course, CPN is very much not a Calabi-Yau manifold. Its canonical bundle is definitely not trivial. But you can decompose CPN into two pieces, one which is a compact Calabi-Yau manifold, and then the complement of that, which is a complete non-compact Calabi-Yau. Okay, so these metrics are also very interesting geometrically. So let me just sort of say in passing, because it's a bit surprising maybe. So if you look at the volume growth, so the geometric properties, if you look at the volume of a large ball, so you fix some base point P, and you look at the volume of the geodesic ball of radius r as r goes to infinity. So this behaves like r to the 2n over n plus 1, where n is the complex dimension of x. So you see it has this very bizarre volume growth. So it's faster than linear, but slower than quadratic. So it's for r very, very large. Okay, and if you look, so that's telling you that there's some sort of collapsing behavior of your manifold. So if you zoom out and look at the tangent cone at infinity, then what you see is just a half line. Okay, so in other words, this manifold looks extremely collapsed in most directions. Okay.
Question.
Yep.
Do you know anything about the isometries that are like? Does this metric have isometries that might be inherited from isometries of x?
So x. So there's not going to be any continuous isometries of x that preserve d, because d is smooth. But there can be automorphisms, which there are isometries of this. There will be in general isometries of this metric, but
Characterize them in terms of p and x.
that I think is not well understood. In general, the uniqueness of this metric is not well understood. So we don't know much. I mean, I think there are conjectures which say essentially that this metric should be unique modulo automorphisms of the manifold, but I think even that is expected maybe not to be exactly correct. Yeah, so
it's easy to see it's rigid though, right?
It's rigid?
Yeah, the metric. Like when you're constructing your Calabi-Yau metric and the complete Calabi-Yau metric, it doesn't have any, in this case, at least again, deformation, which is still rigid flat, right? I mean, if it does, then it's obviously not.
And you mean of deformations of x minus d?
Yeah.
Let's see, can I remember what's known about that?
Yeah, what I mean is that what do you mean by uniqueness? Do you mean like if you look at the moduli of
Yeah, I mean
on x minus d, it's connected, or do you mean it's literally a point?
Either. I don't know. That's part of the problem is how you should even formulate uniqueness, right? I mean, one way to formulate uniqueness is you could say, well, it's unique among all metrics which are asymptotic to the same thing at infinity, and I think even that is not known.
Nice.
Yeah. Right. So the uniqueness is a complicated issue. So the one I'll say, just I'm not going to go into it. The one case where we do understand something about uniqueness is like when x is p2 and d is an elliptic curve, then you can understand these metrics by hyperkähler rotating, and what you get is a rational elliptic surface, and there we have a pretty good understanding of uniqueness. Yeah. Okay, so a natural question which Tian and Yau posed is to understand what happens when D is singular. So what if D is singular? And of course, the simplest possible case is when D is a bunch of smooth manifolds, submanifolds of codimension 1 intersecting transversely. So let's say maybe the first case to try to understand is when D has simple normal crossings. So what does it mean to be simple normal crossings? It means you have maybe two smooth divisors, D1 and D2, and they intersect transversely. So something like this. Okay, and D is the union of these two. Okay, so so this is an open problem. A few years ago, with Yang Li, we constructed complete Calabi-Yau metrics in the case of two divisors with simple normal crossings under an assumption. So let me tell you what that result is. So the theorem. So if D is D1 plus D2, so is a union of two divisors where DI are both smooth, DI smooth, ample, and proportional. So D1 is proportional to D2. So in other words, they both, up to multiplying them by positive integers, they both lie in the linear system of some common ample line bundle. So then there exists a complete Calabi-Yau metric on X minus D. Metric on X minus D. Okay, so right. So let me tell you. So just to differentiate this from the geometry over here, so the volume growth of this metric is again fractional. So it's not integer. So it's 4n over n plus 2. So it grows faster than this, right? But still not very fast. And the tangent cone at infinity, so if you zoom out, so this manifold's quite collapsed, but, I should say the dimension of X has to be at least 3. And the tangent cone at infinity is R2, as a positive orthant in R2. So again, very easy to construct examples. You just come back to this example again, and now you take P to be a product of two polynomials, which are generic, such that the degree of P1 plus the degree of P2 is n plus 1. Okay, and then you look at X minus the zero set of the product, which is the union of the zero sets.
It's a bit counterintuitive though, right? Because you could deform P1, P2, just add a small thing to go to the previous case
Yep.
where the thing is irreducible. But then at that very exact wall crossing moment, your tangent cone at infinity suddenly changes behavior.
Right, yes. So these metrics are not, these metrics do not somehow converge to these metrics in any nice sense.
So you couldn't really solve this problem just by taking the limit of the matrix in the smooth sense.
Exactly, yes, that's right, yeah. Okay, so let me explain how this problem, and in fact the more general problem where you have k divisors, how it connects to optimal transport. Okay, so this is where we go from Calabi-Yau metrics to optimal transport. And maybe at the end we'll go back again, depending on how much time I have. Okay, so here's the reduction to a PDE problem, or sort of relation to a PDE problem. Okay, so suppose we have, so let me describe the general case. So suppose D is a sum of k divisors. K is no more than or strictly less than the dimension of X. Okay, I'll come back to the case of equality later, but for now let me assume this. And assume that these divisors are all, again, proportional over over Q. So they're really all representing up to taking powers. They all represent the same line bundle. So then I can look at the intersection of these divisors. So these this has simple normal crossing, so they all intersect transversely. So then I can look at the intersection of these divisors. This is a compact submanifold inside of X. And in fact, by adjunction, it's a compact Calabi-Yau. Okay, so in particular, Yau's theorem applies to Z. So then, and I won't go through the calculation, but so in a neighborhood of Z, I'll draw the picture in a second. So in a neighborhood of Z, a model for the Calabi-Yau metric for this sort of putative Calabi-Yau metric, so we don't know it exists yet, but the sort of asymptotics that you might expect are determined by a function, so are given by square root of -1 dd bar of u. Okay, where u is a real function. So it's a function of k real variables. Okay, so these xi is basically the minus log of the norm of si with respect to some particular metric, where di are the zeros of si. Okay, so these are real variables. U is a function of these real variables. Okay, and yeah, sorry.
Could you say why you require the dimension to be larger?
Yeah, it's the same here too, right? That I want there to be fewer divisors than there is a dimension. I'll say why. I mean, it's a very interesting question. Here I wanted the dimension to be at least 3 because I had 2 divisors. Yeah. Okay, so right. So you get this function, and you want this function to define a metric. So you get this following. U has to solve an equation. So it has to solve the following thing. So it should be a metric. So that means that the function should be convex, okay, because I'm taking 2 derivatives here, and this is supposed to be a symplectic form, so this has to be a convex function. There's a first order condition which says that the sum of the derivatives has to be positive. Okay, so this maybe it's not obvious. It comes from plugging this into some sort of ansatz calculation, but it will become maybe more clear when I write down the equation. So these are 2 sort of open conditions, and then there's a PDE, which says that the determinant of the Hessian times the sum of the first order terms to the power of the dimension of x minus the number of divisors has to be 1. Okay, so because of this definition of the variables, right? U should be morally valued at least on the positive orthant. So x1 up to xn should be, okay, technically speaking, it's just in the positive orthant outside of some compact set, but let's, so it's in the positive orthant in RK. Okay, because of course, what we're going to do is look for solutions of this equation which satisfy some homogeneity. Right? Okay, right. Okay, so this is an equation. So now I need to tell you, of course, a PD like this is not going to be well posed unless there's some sort of boundary data. So the boundary data, it turns out, sort of experimentally, it turns out that the boundary data should be that this thing, this first order term, vanishes on the boundary of the positive orthant. So another way of saying that is that the gradient map of U is a map from the positive orthant in RK to the upper half space defined by this, this equation. So it's Y in RK such that the sum of the yi's is bigger than or equal to 0. Okay, so where does this boundary data come from? So let me just explain in pictures. Right, this boundary data comes from geometry, and I'll explain why, maybe just in the two divisor case. So why? So this is a slightly slight aside, but so what happens, you have these two divisors, D1 and D2. Let's just look at the two divisor case. And you have this intersection, so it intersects in this variety Z. Okay, and what this ansatz is going to do is it's going to describe the sort of putative Calabi-Yau metric in some neighborhood of Z, but it's not a very accurate description when you go close to D1. So what you get is actually a metric that sort of lives in some sort of region like this. Okay, so some sort of region like this. Right, and then if you want to construct this complete Calabi-Yau metric, you need to say what it is in these sort of non-generic regions. Right, so what happens here? Well, what you expect, so you think about this for a moment, you see that D1 itself is a Fano variety, and if I look at the complement of Z inside of D1, that actually fits the assumptions of the original Tong-Yau theorem. Right, so what you want to do is construct a metric here, which somehow, as you approach D1, looks like some sort of Calabi-Yau metric, which is like Tong-Yau in the D1 directions and maybe a C-star metric in the orthogonal directions, right? And so what we did in the paper with Yang was we observed that, or we showed, that if you impose this kind of boundary data, then as you approach D1, indeed the Tong-Yau metric emerges naturally in the asymptotic expansion of the solution near the boundary. So this kind of boundary data, I mean, it's very natural once you think about it a bit, but it turns out to be the right thing in order to complete the construction of these Calabi-Yau metrics using this sort of inductive approach.
Do you have the uniqueness in the Tong-Yau theorem?
No. Again,
so
yeah.
It might be that there would be another exotic metric here that would give you another limiting metric here. Right?
Could be, yeah. Okay, so so that's where this boundary data comes from. But so now I'm gonna.
Also, the C-star assumption, is it some adiabatic argument that on the
no, actually,
it should be?
No, there's no. So actually, you have no idea what the metric looks like in this direction. What you do is you just know that, or you at least you want the Tong-Yau metric to appear in this direction. So you take the solution to your problem and you asymptotically expand it as you go to the boundary, and whatever you get is the behavior in this direction. Okay, so right. So actually, what it turns out is it's not a product at all. It's some sort of warped product. I mean, as you might expect, it's some sort of bundle of C stars over. Okay, so this now is exactly an optimal transport problem. Okay, so this, a slightly weird one.
Also, sorry, when you get close to Z, your boundary condition is enough, right? You don't need to say anything as you get closer to, over D1, getting closer to
Yeah, you have to quantify exactly how these neighborhoods pinch off. But yes, basically, and these neighborhoods actually are not linear. They sort of go almost exponentially fast. They're very flat. So this is optimal transport. Okay, because what we're doing is looking for a function. So U is convex. The gradient of U maps Rn, or Rk, with the Lebesgue measure to the positive orthant in RK with the Lebesgue measure to this half space. Equipped with a degenerate measure, which is the sum of the yi's, y equals 1 up to k, to the n minus k dy. Okay, so so when you do optimal transportation, right, this is the equation, this is the sort of change of variables equation, which is exactly telling you that u is that nabla u is an optimal transport, is optimal for the quadratic cost. Now, you have to be a bit careful, because actually optimal transportation in this setting doesn't make any sense, because usually when you do optimal transport, you're trying to minimize the cost of something, but the cost of any such thing is just going to be infinity always, right? Because both of these spaces have infinite measure, so one cannot even really formulate this properly as an optimal transport problem. Okay, but as a PDE problem, you can think of it as optimal transport from this cone, right? So RK plus to a half space, which is something like this. Okay, so we've now arrived at optimal transport, and so what we proved with Tong and Yau.
Before
Yep.
that, I'm not very familiar with optimal transport. Why would you say nabla u is an optimal for quadratic cost? What is the cost function here?
So the cost function is okay. So if I was doing this between compact domains,
Yeah.
so then the cost function is the integral of
dy over image of nabla u.
yeah. So it's the cost function is minus x dot y, or in other words, the cost of a map from omega 1 to omega 2 would be it's equivalent to talking about this cost. So dx over omega, where omega 1, where t is a map from omega 1 to omega 2. D mu, yeah, dx, I guess, in this case, if I put Lebesgue measure here. Yeah, and then you require that it pushes forward this measure to whatever your measure is over here. So it turns out, sorry?
That's how you get Monge-Ampère by.
Yeah, so it turns out, so Brenier showed that that this problem for the quadratic cost has it should always have a solution, at least if omega 1 and omega 2 and the measures are reasonable. And that solution is the gradient map of some function which solves the Monge-Ampère equation. Okay, so yeah, but here it's not really, it doesn't fit properly the optimal transport literature, because here the cost is just always infinity, right?
So back again, so whenever you have a Monge-Ampère equation with suitable boundary condition, can you see it as the optimal, like Monge-Ampère equation for some optimal transport equation?
So optimal transport is related with this boundary data, right? We're saying that the gradient map takes one domain to another domain.
Yes.
So Dirichlet boundary data is not associated with optimal transport. Yeah. So it's really like specifying the image of the gradient map. You can think of it almost like a Neumann problem, right? Really, you're saying something about the gradient of u on the boundary.
Yeah.
Okay, so what we proved was that that this problem has a solution. So there exists homogeneous solutions to this problem. In fact, what we proved is sort of slightly more general, in the sense that, you don't necessarily need this to be an orthant. But anyways, okay, right. Okay, so this theorem sort of constructs the generic asymptotics of these putative Calabi-Yau metrics on the complement of k divisors. So the piece that's missing right from the construction is to understand what happens in these non-generic regions. Okay, so let me say something slightly more before I go on to more optimal transport, which is that if you remember at the beginning, I made this assumption that the divisors were all proportional. So in general, you can try to do the same thing. Okay, the same sort of reduction works without assuming that the divisors are proportional. So if minus kx is the sum of a bunch of divisors, but they're not proportional, so di's are ample, but maybe not proportional, then you get another optimal transport problem. Okay, so then you get a polynomial p of y, which is homogeneous of degree n minus k. N minus k. And this optimal transport problem now becomes a map from P, or from this positive orthant to this convex cone where P is positive with the measure P of y dy. Okay. So in this case, so the case of proportional divisors is the case when this P is just a power of a linear function, right? So you get it's a special case. Okay, so now I want to talk about this this sort of more general kind of optimal transport point of views, because it turns out that these sort of homogeneous solutions of optimal transport maps or optimal transport problems between convex cones are actually really fundamental in the regularity theory for optimal transportation. So the next 30 minutes I will talk about optimal transport. And if there's time, I'll come back to the Calabi-Yau.
Just on your theorem, you essentially proved the Monge-Ampere equation has a solution, right?
Yes, exactly. Yeah. But again, I mean, I should say, even this we don't know uniqueness of. Yeah.
That's interesting.
Yeah. So maybe I can say a word about how this goes. So the idea is that you reduce this problem. So you're looking for a homogeneous solution, right? So on this orthant, right? If you're looking for a homogeneous solution of this problem, it's defined by a function on the simplex, right, on this triangle. And so you reduce this to a compact problem. Okay, so you reduce by homogeneity to a problem of the following form, which is again a Monge-Ampere kind of optimal transport type problem, but it has a very bizarre boundary data. So you reduce to a problem that looks like this. You get a function phi on P. Okay, so P is, you can imagine that this doesn't need to be an orthant. It could be a cone over any compact set. So this is P. Oh, sorry, I shouldn't call it P. Let's call it, because I already used P. So let's call it Q, convex set, compact convex set. Okay, so this is Q. And if you do this reduction, you compute that this solving this problem, finding homogeneous solutions of this problem, is equivalent to solving this equation, determinant of d squared phi is 1 over phi to the k plus 2 minus phi star to the n minus k on P. I'll say what phi star is in a second. With this weird boundary data, so phi star is like the Legendre transform of phi. So it's x dot nabla phi of x minus phi of x. And then with this weird boundary data, which is not that phi is 0, but that phi star is 0 on the boundary of P. Okay, so it turns out, so if you write this instead in terms of the Legendre transform, so there's always this duality in Monge-Ampere that you can introduce.
So P is Q here, or?
Oh, sorry, P is Q, yeah, P is Q.
And now you have a Dirichlet type boundary.
Well, it's, yeah, so it's Dirichlet for the Legendre transform.
That is correct.
So what's weird, so you can write this in terms of an equation for phi star. And then, so let me tell you what you get, because it's quite interesting. What you get is, so if we let, if V is phi star, the Legendre transform, then taking the Legendre transform inverts the Hessian. So this is 1 over the determinant of d squared phi. So what you get is the determinant of V is V star to the k plus 2 times minus V to the n minus k on the image of the, so the Legendre transform is defined on the image of the gradient map, which by this boundary data is the set where V is negative. So you get something like this. And then you have this, also this gradient map component. So the gradient map of the sublevel set where V is negative should be Q. So actually, it turns out, so you're basically solving a more standard Monge-Ampere equation with Dirichlet boundary data, but then also imposing that the image of you're imposing 2 pieces of boundary data. You're solving both the first boundary value problem, which is that V is 0 on the boundary, and simultaneously the second boundary value problem, which is specifying the gradient image. So this is a very overdetermined problem, except that this domain is a free boundary, right? So this becomes a variable. This sublevel set of V is a free boundary. Okay, so it's like it's a problem where you want to solve simultaneously the first and second boundary value problems for Monge-Ampere, and you do that by letting the domain become a variable. So this is the problem that we solved, and then actually, let me just mention in passing that Benji, my student Benji Firester, and I solved we showed that you could solve, in fact, very general classes of Monge-Ampere equations with this kind of mixed first and second. So there's a very general existence theory. For this type of Monge-Ampere equation, this type of free boundary problem. It's a new, as far as I know, a new kind of free boundary problem, but it's very natural when you think about it, because the two most natural boundary conditions in the study of Monge-Ampere are to specify the gradient or fix the function to be 0 on the boundary, and this is somehow doing both of those.
So again, now here you think about the variables as what time?
Yeah. So the sublevel set of V. So the domain is the sublevel set of V. So the domain is unspecified because it's a function of the input, right? I mean, you can also just think of it this way and then say that V is defined on all of Rn, but that its gradient image is Q. And then the sublevel set of V becomes the domain. Okay, right. So this has a very, so so anyways, we can solve this problem. Okay, now let me explain the relevance of this stuff to the, optimal transportation. Okay, so what is optimal transport? So let me remind you. So you start with some convex domain, say. It doesn't have to be convex, but let's make our lives simpler, assuming everything is convex. So we have some convex domain in Rn. So this is the sort of, in some sense, the most restrictive version of this problem, but. And they have measures on them, d nu and d mu. Okay, and you imagine that these two measures are describing the distribution of some debris, right? That's the classic thing. So you have some pile of dirt inside of omega 1, and now you want to use that pile of dirt to build some structure in omega 2, right? Which maybe like the pyramids, right? You want to build the pyramids. And you want to do that in the cheapest possible way. So you're looking for a map T from this from omega 1 to omega 2. So first of all, there's a compatibility condition, which is that the amount of debris you need to build the pyramid should be equal to the amount that you have. So you have to assume that the volumes of these two measures are the same. Okay, and then you want to minimize some cost. And maybe the most natural cost is the one which is just the distance between 2 points. That turns out to be pretty hard. So the next most natural cost is, so you want to minimize among all t, which such that the push forward of d nu is d mu. So that means they transport this pile to this pyramid, and you want to minimize the cost, which is, say, 1/2 integral over omega 1 t of x minus x squared d nu. Okay, so this is saying I want to do this in a way which somehow, if my cost is a function of the distance that I transport each point, the square of the distance that I transport each point, I want to minimize that cost. Okay, so in the 80s and 90s, I want to say, there was, so Brenier showed that, and I guess also Caffarelli, so some combination of the work of these two, showed that if d mu, or if these two measures are, say, absolutely continuous with respect to Lebesgue, d mu is g of y dy, and let's assume these these functions are bounded from below and above on their domains. Okay. And omega 1 and omega 2 are convex. Then this optimal transport map exists and is given by the gradient of a function. So omega 1 and omega 2 are convex domains. Then T exists, in fact, uniquely, and T is the gradient of U, where U is a convex function, and it solves this Monge-Ampere equation. Determinant of d squared U is f of x over g of nabla U of x, with the gradient map of omega 1 being omega 2. Okay, so this is the the sort of origin of the connection between Magen-Pair and optimal transport. And then after so as sort of part of Caffarelli's work, following this sort of explosion of interest, there was a lot of work in the regularity theory, which maybe I will. Of course, this is a huge subject, right? So I'm not going to pretend to say anything complete about it, but it was sort of extensively developed in particular by Caffarelli and others in the 90s. So in particular, in 1992, Caffarelli proved several results which describe the regularity theory in quite a lot of generality. Now, I won't go into what's known, but what has been a sort of open problem is the boundary regularity theory. Sort of open problem. Has been boundary regularity theory. For optimal transport when omega 1 and omega 2 are not strictly convex or not uniformly convex. So uniform convexity is the statement that you can touch the domain from the inside and the outside by some ball or by some pair of balls. So for example, polytopes are not uniformly convex. So uniform convexity is something like you have some huge ball and some small ball, and the domain sits in between these two. Okay, so this case, for example, optimal transport between polytopes, right, has been an open problem, boundary regularity for optimal transport maps between polytopes. So, for example, if d mu and d nu are both Lebesgue measures, or Lebesgue, and omega 1 and omega 2 are polytopes in R2, so in 2 dimensions, then the boundary regularity, essentially the best, then C1 1 minus epsilon boundary regularity was established by Savin and Yu in not in the what year? Let me see. I don't remember. Not so long ago. The last 5 years, say. Okay, so that's kind of just to give you an idea of this sort of difficulties, right? Caffarelli's work was in the 90s, and this is still sort of an ongoing thing. It was 2020, right? 2020. Okay, so recently, right, last year, 2025. I won't say, since again, not to talk about regularity theory in itself, but in 2025, joint work with Fried Tong, we introduced a sort of new approach or new tool, which is a monotonicity formula. Monotonicity formula for optimal transport maps in this setting, quadratic cost, which in particular implies that, which tells you, the upshot is that this monotonicity formula says, it tells you that suitable rescalings actually converge. I'll draw a picture in a second. Suitable rescalings converge to homogeneous optimal transport maps.
So is it like a tangent? Oh, no.
Exactly, yeah. Right, so what this tells, why is this useful? Right. So if you want to, in the geometric regularity theory, for example, for minimal surfaces or for Einstein manifolds, right, often direct methods you cannot prove very much by direct methods, by proving direct a priori estimates, right? Instead, you study the regularity theory by contradiction arguments, right? You say, okay, suppose something bad is happening, I blow up, I get a tangent cone, and if I can rule out various behaviors of tangent cones, then I can deduce regularity theory from that. So this monotonicity formula allows that approach to be used for optimal transport. Okay, so in particular, right, so for example, a corollary, well, it's not a corollary, but as using this monotonicity formula, again, I won't state things precisely, but we generalized this, we extended this Savin-U to arbitrary dimensions. So the boundary regularity to so C1 1 minus epsilon to all dimensions. So it's quite a powerful tool having this monotonicity formula. But one thing it also tells you, okay, so let me explain that. So draw pictures, right? You have some domain, let's say, let me draw an interesting domain, right? Maybe it looks like this, some interesting convex domain, and it's mapping to some other interesting convex domain. And let's say I know that this point maps under Nabla-U to this point. Okay, and I want to understand the regularity of this function. So then after rescaling, so what I do is I look at this function on sort of smaller and smaller sets, as appropriately chosen sets around this point, and I rescale. And after doing this rescaling, right, so you sort of zoom in, what you might see is an optimal transport map which takes the sort of tangent cone of this convex set to the tangent cone of this convex set, something like this. Nabla U tilde, and U tilde is homogeneous. U tilde homogeneous. Okay, so now in order to understand the regularity theory, it becomes very useful to understand both the existence and non-existence.
Is it subset of the image, or the image is literally equal to the tangent cone of the?
So you have to be a bit careful here, because actually the cone that you get out of this rescaling might not actually be the tangent cone of your original convex set, but it does map surjectively onto some convex cone. Okay, so right, so it now becomes very interesting to understand from the regularity theory the existence and non-existence of homogeneous optimal transports maps between convex cones. Okay, because if such maps exist, then that tells you something about, so say between the tangent cones of these two convex sets, then that tells you something about the regularity theory. And conversely, if they don't exist, then that also tells you something about the regularity theory. Okay. So now, so in dimension 2, it turns out, so dimension 2 is the first interesting example. So if I consider two cones, and so now I have C1 and C2, cones in R2, convex cones in R2. And if I consider the case with Lebesgue measure, so the measures are dx and dy, then in fact we, again in the paper with Fried, we classified all possible cones. Okay, there are essentially three pictures. In fact, I won't write it all, or I won't write out the words. I'll just draw the pictures.
By all possible cones, you mean all solutions to Monchal?
Yeah, all possible pairs of cones, C1 and C2, for which there exists a homogeneous optimal transport map from one to the other. So the simplest case is when the cones are just half spaces. Okay, so I'll draw them in the same space. Although, okay, so basically you can have two half spaces as long as their normal vectors have positive inner product. So N1 and N2, N1 and N2 have to be positive. Okay, so then you can also have the case where you have two proper cones, and C1, which I've drawn as orange, C1 is contained in the dual cone of C2. So this is the cone which is, in other words, these vectors are the normal vectors to the edges of C2. So this is what I would call the strictly oblique case. Okay, so case 3 is when the reverse thing is true. So C1 contains the dual of C2. So C1 contains the dual of C2. So C2 dual is contained in C1. Right, so C1, C2 dual. Okay, and then the other case is when the cones are just dual to each other. And I should say all of these containments are supposed to be proper. They're somehow not supposed to touch on the edge. So really it's sort of a strict containment. So 4 is when C1 is equal to C2 dual. So you can imagine that this case essentially is just the case where you have two orthants, C1 and C2. Right, of course, in this case, the identity map is the optimal transport map. Okay, so let me point out one situation which you do not see here is the case when you have an orthant mapping to a half space. So note, there's no solution in the case when, let's say, C1 is the positive orthant in R2, and C2 is a half space. Which is exactly the case of this problem, of this Calabi-Yau problems, when you have two divisors in dimension 2. So e.g., this is exactly the problem that arises for P2 and two divisors. Right, because so this comes back to that non-existence result that you asked about, right? So yeah, so in this case, there's no solution. And we actually, Yang and I already knew that in our paper, because you can just check, you can check that there's no solution. I mean, that's also what we did here, I guess. Okay, so then, so this is in dimension 2, but you can ask what about more generally, right? And then in that direction, in work with Benji, oops. We showed that actually this case 2 that I erased, we generalized the strictly oblique case, the case when C1 is contained in C2 dual, to any dimension. So in fact, if you have 2 convex cones which satisfy this strictly oblique condition, then solutions will exist in any dimension, right? And so one thing we're trying to understand at the moment is a sort of, I mean, what one could hope for, probably too much to hope for, but what one could hope for is a sort of complete classification in all dimensions of all pairs of cones which can possibly admit these homogeneous optimal transport maps. And that's probably too much to hope for, but anyways, one can try to develop a better understanding of when these optimal transport maps do and do not exist. So, right, so for example, in dimension 2 now, we can, because we have this classification, at least for the Lebesgue measure, I mean, you can essentially say everything you could ever hope to say about the regularity of optimal transport maps between polytopes and R2. So in some cases, right, when you know that the optimal transport map functions in such a way that so for example, right, if you have an optimal transport map from a square to a square, well, here, of course, you have the identity map. It's going to be C infinity up to the boundary, C2 alpha up to the boundary, for example. But if I have an optimal transport map from a square to a circle, then in fact we know it cannot be C11. Because if it was C11, you would see, after blowing up, an optimal transport map from an orthon to a half space. And we know that such a thing doesn't exist. So this can be C infinity, and this is not C11. Because there's no tangent cone. Okay, so, all right, so I will not have time to go back to Calabi-Yau's, but anyways, I'll stop there. Thanks.
So because here you think about tangent cone already in this setup that you have a map and stuff, there's no notion of multiplicity, right? Everything is just multiplicity 1.
Right, because I mean, from the point, if you want to think of it in terms of minimal surfaces, this is like a graphical minimal surface.
Yes. And also, in this case, rather than R2, if you were to think about C, could you think about the equation as a Cauchy-Riemann type equation? Like, because I think motion per case dimension usually can be written
in C2 instead of R2?
C.
In C.
Yeah, rather than R2.
Oh,
Okay. I was just wondering if that's how you thought about it.
No, we didn't. Yeah.
Also about the whole convexity, do you usually consider convexity because it's simpler to deal with Motion-Ampere equation, or it's naturally the motivation from your motivation that you think about?
So, right, so that's a good question. So certainly in the geometric applications that I'm interested in, convexity is you always get convexity. From the optimal transport point of view, it's where the regularity theory is best understood and sort of least complicated, right? So there's this classic example where, you imagine you take an optimal transport map from a ball to a union of 2 balls or something. So such a thing obviously cannot be, like the gradient cannot be continuous, right? Because then the image would be connected. But what Caffarelli sort of showed was that if you take this and you just put a small neck between these 2 things, that actually still you cannot have the gradient map still has to behave badly, basically. If you do this, sort of nothing too much changes. So if you have something, so this is very non-convex. So in this case, the regularity theory is less than C1 alpha. So somehow when you go to the non-convex case, the regularity theory becomes much more complicated. Yeah, and in the monotonicity, so certainly the convexity of both the domain and the image, at least in the neighborhood of the point, that enters the monotonicity formula. Because the monotonicity formula, what it tells you is that after blowing up, it tells you that the function becomes homogeneous, it solves the optimal transport problem, and that the domains become convex cones. So there's many terms in the monotonicity formula which have to vanish on a constant solution, and they involve the convexity of the boundary. So if you have non-convex domains, then this monotonicity formula will not work. Yep, that's a good question. I mean, of course, you can always, I mean, maybe the other thing to say is that, you know, even if I have an optimal transport map from the disk to this, I can always view this as a convex domain just with the measure being 0 outside of here. So there's some relation between, it's not just the convexity of the domain. This also has something to do with the support of the measure.
It depends a bit on your boundary condition. Yeah.
Any other questions, Tristan?
Could you explain more about your monotonicity formula and how to define this monotonicity formula?
Yes, sure. I can say quickly. Yeah, so this is like a whole second talk, so I won't, I'll try to do this in 2 minutes. So basically, so for when the cost is minus this 1/2 x dot y, then this optimal transport map, you can think of, so Nabla-U solves optimal transport. The optimal transport problem is, let's say with Lebesgue densities, right? Let's say Lebesgue, just for simplicity. If and only if the graph inside of R2n is maximal, is area maximizing for the metric which is the pseudo-Riemannian metric, which is basically the Hessian of this function. So in this case, it looks like identity, identity, and 0. Okay, so it's basically the Hessian of C. Right. Okay, so then what you can do is you can look at, so what are the geodesic balls for this metric? Oh yeah, so it's maximal and it's space-like. So the metric restricted to this graph is Riemannian. So then what you can do is you can, so the geodesic balls for this metric are the sets x dot y less than r squared. Okay, so around the origin. And what you can do is look at the, the standard volume ratio. So you look at the function, which is the volume of the graph in BR divided by the sort of expected volume. And it turns out that this, so this is for the Lebesgue measure. For other measures, then this is a different power here. But for Lebesgue measures, this is what you get. And then it turns out that this is monotone decreasing. As a function of or non-increasing, right? And you get equality exactly when all of these things I said are true. So that's a homogeneous solution defined on a convex domain with image being or convex cone with image being a convex cone. So it really comes from this sort of from this is I should say this is all due to Kim McCann Warren. This is not Kim McCann Warren. This idea that you can view optimal transport maps as they're essentially calibrated submanifolds in this pseudo-Riemannian space. And then what we showed was that, yeah, I mean, our stuff applies very, very generally, but in the simplest case, when the densities are Lebesgue, then our homogeneity statement is just this one. So geometrically very natural.
So you kind of translate this into the multi-empiric case, the optimal transportation case, this monotonistic formula.
I mean, yeah. So basically, yeah. So basically, we did this calculus. I mean, really, all we're using is that that this graph is area maximizing. I mean, even actually, it probably just depends that it's maximal, not area maximizing. Although it turns out to be area maximizing as well. Yeah. So it has zero mean curvature. That's essentially the calculation. It really looks very much like the usual thing.
I didn't see how do you translate this to the multi-empiric case, the formula.
How would you write it in terms of?
The minimal surface monotonous formula. How do you translate it into the multi-empiric case?
Well, you just use this fact that the graph of U is an area maximizing surface. So this is the monotone quantity. So it's like the volume of the image of the gradient. You take X cross the volume of the image of the gradient map, and yeah.
The calibrated condition leads the merge up equation, essentially.
Yeah, exactly. Yeah. Yeah. So this is some sort of like. I mean, this is actually. I think the motivation for this came from Hitchin's work on moduli of special Lagrangians. Actually, in some sense, yeah. Anyways, yeah, beautiful. It's a really beautiful idea, and this monotonicity formula, it's a very natural extension of their ideas.
Any last questions? If not, let's thank Tristan again.
Thanks.